Hey Math All-Stars, it's Dr. Conklin here to do a video with you on page 8 in our new similarity packet. If you could get that packet out. Again, if you don't have it, we got to figure out a way to get it to you because there's a lot of graphs in this packet, so please be in touch with us. But we are on page 8 today, and you will not find a picture of my son Charlie and cat Alvin, in this packet on page 8, but I'm going to use that to talk about a little bit. So when we look at this unit, there's some really important terms, and we're actually going to define them on this page. So I know you guys already know what a transformation is. What is a transformation? A transformation is a move or change in a shape. Okay, so you should be writing this down, my loves, right? And actually, really the only thing we're asking you to hand in today is a picture of notes. We have 3 kinds of transformations we've already learned. Really, we've learned all 4, but we're really going to focus on... Oh, no, we have learned this other one. I'm going to put one on the side. So we have our friend reflection, rotation, which is our big capital R. We also had our translation. And then I'm going to sort of put this one to the side here. And he's a little special, and that's our dilation. Okay? Why is dilation different? And I know you guys already know this. These 3, reflection, rotation, translation, are all rigid motions. Dilation, not a rigid motion. Okay? So that sort of brings us to our second keyword we're reviewing here. And that's what are isometric transformations. So isometric means rigid motion. So we have our little r for reflection, our big R for rotation, and our T for translation. Those 3 are isometric. Now, this is the word we're really working towards today. What are similarity transformations? Now, before we can jump into that, let's define what the heck is similarity. And what I'm going to ask you guys to do is to first put the symbol next to it. This little squiggly line right here, maybe put a box around it so you don't lose it. You don't need the box part. But this little mark here, the squiggle, that means similar. So if I said this triangle is similar to another, I don't need to write the word similar out. I can just do the squiggly line. Let's talk about what similarity is. So I'm going to look at my cat and son Charlie. You guys have probably seen Charlie many times wandering around when I'm trying to teach lessons if I'm working at home. If I start with this shape, and let me just copy it, I'm going to paste it right here, if it will let me. Oh boy, this isn't going to work if I can't paste it. Yep, yay. Okay, these shapes are actually congruent. We have Charlie and Allie, and Charlie and Allie. This is the same exact shape, right? Like I can move these around, and these sort of lay right on top of each other. Does everyone see that? Now, what if I take this picture and I want to make like a wallet-sized picture? So I'm going to cut it in half. Oops. It's going to let me. See if it'll let me move it around. Okay, so I'm going to take Charlie and Allie, and I'm going to make them half as big. Now notice what I did, guys, is I didn't just make one part of Allie and Charlie half. Let's say this was 10 centimeters. I made this 5 centimeters. Notice what I did is I shrunk them down. Let's say that the length of this was 12 centimeters. I shrunk this to 6 centimeters. I have to use the same proportion to shrink the picture, or the picture will change and won't look the same, right? Okay, so let's take this idea to a different level, and let's look at a trapezoid here. So I have a trapezoid. Again, you might want to draw this picture in your notes so you have it, and I'm just going to make a copy of this. Okay, these are congruent. Do you guys see that? And actually, congruent shapes are similar. They're just exactly the same, right? Now, let's say I take this shape, and I'm going to make it half the size. Does this shape still look like the same exact shape? Yeah. I mean, it still looks like a trapezoid, right? Let's pretend that this is 10, this is 16, this is 12, and this is 12. Well, if I made it half the size, this would have to now be 5. This matching or corresponding side, if you will, is going to be 8. And then think to yourself, what are these sides going to have to be? Well, again, if we're shrinking it by half, these have to be 6. So that's sort of the idea behind similarity, is that you have something that's the same shape, but it's changed size. So they're definitely not rigid motions because they've changed size, but their shape is preserved, okay? We can also do the same thing with making things twice as big, but I want to show you one other thing that a lot of kiddos sometimes forget about similarity, is that if we have shapes that are similar, no. Okay, I'm gonna just copy this, paste it. I gotta get Mr. Fields to show me some of these tricks. I think I copied it, didn't I? Copy. Oh dear. I really did practice this ahead of time, guys. Oh yeah, okay, paste. All right, so again, these shapes are similar because they're exactly the same, but they're just congruent too. Now, what happens if I wanna make this bigger, okay? So I'm gonna make this bigger, but what happens if I take one of the angles and I change the angle measurement? Oh, no, I didn't. Do these look like trapezoids? Do these trapezoids look the same anymore? They don't, okay? So we're not allowed to do this. What I just did, how I changed this angle, is not allowed. So angles have to be the same, right? So this angle has to be the same as this angle. This guy has to match with this one. This guy has to match with this one. Oh, how many did I count? Okay. All right, so let's write that definition, and I know it took me a little longer to explain, but similarity, 2 things. We have to have all corresponding angles congruent. Second thing is sort of like if we go back to our picture of Charlie and Alvin up here, these have to be proportional. 5 and 10 are the same ratio as 6 and 12, right? They're both 1/2. So all sides are proportional. All right, so that's really the important definition for today. And let's put that together with what we've already learned. You can take this trapezoid and I can make him bigger. So that means a similarity transformation means I have a dilation at least. And it could also include, guess what else? Well, let me look at this trapezoid again. Let's say I took this big trapezoid after making it, blowing it up, and I rotated it 180 degrees. See how I'm doing that? About a point. Oops. Right? Or let's say I took this and I made it bigger, right? So it started like this. Oops. I made it twice as big, and then I translated it. That would also be a similarity transformation. So when you hear that word similarity transformation, it means you're doing a dilation and one of the 3 things. Ooh, bell ringing. Translation, a rotation, and a reflection. And you only have to do dilation, but a similarity transformation is basically saying, hey guys, guess what? We're doing a dilation and we're gonna probably add something else in. Okay, and then really quick, a similarity statement. This is a similarity statement here, my friends. It's when we say 2 triangles are similar, or really any shapes are similar to each other. So 2 shapes are similar. Okay, so this works almost like what we had before. Remember that little symbol here means similar. If I look at triangle ABC is similar to triangle MRG. M has to be in the same space as A for the angles, right? Now, this can get a little trickier with the proportion. This is what Miss Vala did with you guys yesterday. So here's RG, and here's BC. Do you guys see how those are in the same spot? RG to BC. Okay, so we went from the second triangle to first. Now let me pick a different color. GM, that's on the beginning and end. That has to match up with CA. Okay? And then let's do the same thing. So try this one, guys, right now. And try this one. So same idea. Triangles are similar if the angles are congruent. So notice these are congruent, the angles. But what do you notice about the sides here? We're not saying the sides are congruent. We're saying the sides are proportional. That's what we're setting up here, is proportions. Okay, so let's try this one. Here's T. That's going to match with angle Q. So again, the angles have to be the same. And then same thing here. ST matches with, and again, ST's here. If I look at TV, do you guys see how TV is the same segment in, or a different segment in the same triangle? And then let me highlight here, WQ. Oh, so that goes with the yellow ST, right? These two match. So what piece am I missing down here? TV goes with the second two. So QY is going to go down here. Okay, so that's most of page 8. I'm actually going to go back in time. Hey, Charlie. Hey, Alvin. I don't know if I told you guys. I think I told some of you the story about Alvin. We adopted Alvin from the Manan shelter, and we thought Alvin was actually a boy when we adopted her, but Alvin actually is a girl when we got her home. So now her name's Allie. So she's a good kitty cat, though. All right, so page 4 sort of has more of the formal definitions for you guys, and we're going to look more at finding missing sides in future lessons. But let's just look at example 1 really quick, and I'm just going to look at B. And I want to match this up. AC matches up with DF. So what's the ratio here, right? If these are similar, that's what this little congruent statement is telling us in our similarity statement. The ratio is 7 to 14. So basically, this is the smaller triangle, this is the bigger one, in order to find the matching side. So let's look at, like, B to C is right here. Where's E to F? In order to get from 8 to find this side, we need to take it and multiply by 2. Okay, and then if we're working backwards, here's AB, here's DE. In order for these sides to be proportional, I need to take this 20 divided by 2 to get 10. Okay? All right, and then last thing we'll talk about, I actually want to do maybe just one of these because we're running short on time. Let's go to page 5. Again, thanks for being flexible today, guys. How does triangle ABC, that's the top one, turn into the bottom triangle MNC? Okay, and again, this is our similarity statement. These triangles are similar, which means the angles are all congruent to their corresponding angles. So like A has to match up with M, B has to match up with N. So how can we do this? Well, again, this says use tracing paper. We're just sort of going to do the best we can, but we're starting. How does this turn into this? Well, we know it's a dilation because it has this word similarity transformation. So we're dilating. Now, what point are we dilating about? Well, C, because basically they're opening and closing around C, right? So we're dilating about point C. And then what I'm going to do, and again, it might be easier like use a pencil. I'm going to take MC and I'm going to see how many of those, oops, if I copy this, oops, I want to do the whole thing, sorry guys. Sorry, I want to keep that little green guy. How many of these fit in to AC. So if I count 1, 2, 3, and we actually, when we get into compasses, we could use our compasses. So be careful. We're not dilating by a scale factor of 3 because we're going ABC is big to small. We're dilating by a scale factor of 1/3. And then how are these moving? Well, this is when you might want to remember our good old friends of patty paper, right? So I'm going to take this. How do I get A to match up with M? Well, I'm going to have to take what? And I'm rotating this around. So follow A with me, guys. Right, I put that little green. Maybe I'll make it a different color so you guys can see it better. Here's A up in the corner. I'm rotating it about what point? About point C, and I'm shrinking as we go. So that's going to be 2 sort of turns of the clock if you're using your patty paper. Okay, so I'm rotating about point C 180 degrees. Remember, it doesn't matter if you go left or right. So notice they gave us this hint, write a similarity transformation. A similarity transformation means we have a dilation, which we did find one. That's the worst star I've ever drawn, sorry guys. And then we had our rotation. Okay, I think I'm gonna leave it there for today. Please hand in a copy of your notes and keep up the great work. We're an email away if you guys need anything, okay? Have a great day.